Hello and welcome to another video. And if you've been following my channel and you're wondering why I didn't make videos for like Monday through Fridays, because I was at a company event in SF, so I only just had like a work laptop and I didn't want to download OBS and use stuff on there. So I still did the problems to maintain my streak on the work laptop, but I didn't like make any videos or anything. But I'm back now, so we can do videos again. So we're going to be doing this one, which is remove max number of edges to keep graph fully traversable. And you have an underacted graph of n nodes with Alice and Bob, and you have three types of edges. Type 1 can be traversed by only Alice, type P can be traversed by Bob, and type 3 can be traversed by both. So the edges are type, and then the two nodes they connect. And you want to find the maximum number of edges you can remove such that after removing them, the graph can be fully traversable with Alice and Bob. The graph is fully traversable by Alice and Bob. If starting from any node, you can get to any other node. Return the maximum number of edges you can remove, or -1. So the first thing to say is, let's say you had a problem that was just like given a bunch of nodes and a bunch of edges, make a fully connected graph. And so there are problems like that. That's like make a minimum spanning tree, which is basically like a graph that's fully connected with the minimum, like if you add up all the edge values, it's the minimum. But here, all the edges are like, there is no weight, so all the edges are just like, you can say length 1. So it doesn't really matter which edge you pick first. But what does matter is some edges are only traversable by Alice or Bob. So what you're going to want to do here is you're going to want to use the type 3 edges first if possible, because a type 3 edge is always going to be either better or the same as the other ones, because they could make a connection for Alice and Bob, which would be better than just one edge. Or they can make a connection for Alice, which would be the same as an Alice edge. Or they can make a connection for Bob, which is the same as a Bob edge. But it's never going to be worse using a type 3 edge. So the strategy can just be like, let's just first try to use as many type 3 edges as we can. And then after that, we'll try to use some other edges. So for this example, let's actually draw this graph for Alice and Bob. So let's say we have like Alice on the left and Bob on the right. So we have like this. I think I did that wrong, actually. Yeah, so 1, 2, 4, 3. Actually, let's also not draw the edges. Let's just draw the nodes. So 1, 2, 3, 4. And the same exact thing for Bob. So maybe like over here. And then for each of these edges, we're basically going to say, like, does this edge add anything for us? So let's just look in the picture. Let's start with this edge here, this blue one. So this blue one will connect 1 and 2 for both Alice and Bob. So this does do something. So we're going to use that one. Does this one add, this other blue one, right? We're going to use type 3 edges first. Doesn't matter which one you try first, this one or this one. So now let's say we go with this one. So does this add anything? Does this connect something that wasn't connected before? And something that's not connected before, the way we could check that is a union find, but I'll talk about that later. So this one also helps. This makes these connections. Now let's look at the edges for only Alice and then for only Bob. So let's start with this top one. Like I said, it doesn't matter which order. Actually, let's go left to right, starting here. So 2 to 4. So we're gonna look for, let's call this Alice and let's call this Bob. So is 2 and 4 already connected? No, it's not. So we need that edge. Okay, what about this one? 1 and 2. 1 and 2 is already connected, so we don't need this guy. What about 1 and 3? 1 and 3 is already connected as well, right? You can go here. And I'll show you how to do that using union find. And yeah, I would say, like, if you haven't done union find at all, try to find like just examples of using union find first, because it can be a prereq for doing this problem. So that one is not needed. This one, 1 and 3, 1 and 3 is also not needed, right? And now we have the edges for Bob, which is just 3 and 4. So 3 and 4 does need to be connected. So these are the two redundant edges. So it's 1, 2 for Alice and 1, 3 for Alice, which is that. Now also, after you use all the edges, like the graph, you have to check, like, is Alice fully connected and is Bob fully connected? And if not, you want to return -1. In this case, they are fully connected, so we're good. Okay. So here's example 2. I guess it's the same thing. So let me copy this guy and just bring it down here. All right, maybe make it a little bit smaller. There we go. Okay, so here we'll have Alice, a little smaller, and Bob. Okay, so Bob and Alice. So once again, we're going to start with the blue ones. The word doesn't matter. So does this edge do something? Yes, it does, because nothing's connected yet. So this will work for both of them. Is this edge also needed? Okay, now let's look for Alice. 1 and 4. So 1 and 4 are not connected, so we need that one. And then for Bob, 1 and 4 is also needed. So every edge was needed here, and these graphs are now both fully connected. Like you can go from any node to any other node. So in this case, we can't remove anything. Now finally going to the last example. Let's delete this, and go down here and make this smaller as well. Okay. So same thing, Alice, Bob. So let's start with the blue one. So the blue one is needed. Now let's do the red one for Alice. This is also needed. And the one for Bob. So this is all the edges we had, but these graphs are not fully connected, right? This 4 is all alone for Alice, and this 1's all alone for Bob. So they're not fully connected. So we just return -1. But basically the strategy is you go through all the edges. First of all, so what we're going to use is we're going to use a union find. So we're going to make a union find for Alice and Bob. And the union find is just going to be basic union find. That's going to have n edges. And anytime we use a blue edge, we will connect. So basically, let's write this down. So union find for Alice and Bob. And like I said, I'm not going to explain union find in detail because there's a bunch of problems for that and this would get too long. So I would start with a simple union find problem before doing this because there's going to be like union find with other stuff here. So we're going to first go through type 3 edges. Then if that edge didn't connect, like basically you can just check. So union find typically has like is connected, or you can do it in the union. You can just check like is that are those two nodes that you're trying to connect connected already? And so if Alice and Bob are already connected for that edge, it's redundant. Right, so we're going to prioritize type 3 edges. If Alice and Bob are already both connected, like let's say we have this, for example. So let's say we have a graph like this, already done. And then we have a blue edge. So this is like a fully connected graph. Not quite. I guess it needs to be, let's change it a little. So let's just say it's like this. There we go. That's fully connected. Okay, and let's say we get an edge from 1 to 3. That's blue. So we're going to check, is this redundant? Yes, it is, because this whole thing's already connected, and it's also connected here. So if we get a 1-3 edge that's type 3, this will be unnecessary, and that will be one that we won't be using. And then the next step is go through other types of edges. And it doesn't matter in which order if you use type 1 or type 2 first, because they're mutually exclusive, right? Like type 1 only works on Alice and type 2 only works on Bob. So go through other types of edges, check if it does anything. So for example, if we have a type 1 edge for Alice that connects 1 and 4, let's say, we'll just say like, are these connected already? If it is, we don't need that one. Same thing here. And that's kind of the main thing. Now the last part is we have to check, is this whole thing fully connected? And that's the last part for the union find. So basically for a union find or for any graph, anytime you add an edge that doesn't form a cycle, so when you first start, we have n components. It's called like, you can have n connected components, n disjoint sets, whatever you want to call it. Let's just say we have n connected components. And what I mean by connected components is when a component is connected, you can go from any node in the component to any other node in the component. So this would be like one connected component. But when we first make all our nodes without any edges, we're going to have n connected components, right? Because every node will be its own component. Then every time you add an edge that's successful, that's not a cycle, you have one less component. So for example, we have 4 here. If we add an edge like this, now we have 3 because this is 1. We took 2 components, made it 1. Anytime we add another edge, we have 1 less, no matter where we add. So we just have to check how many connected components we have. So we can start off with n, and then every time we add an edge, we can just subtract 1. And so we're going to add n minus 1 edges, and then we should have 1 connected component for Alice at the end and 1 connected component for Bob. Or you can just keep track of how many successful unions you had, and if you had n minus 1 successful unions, then the whole thing is connected. Either one is fine. It's like the same thing as a tree. Like any tree has n minus 1 edges, because in order to connect everything without a cycle, it takes n minus 1 edges. You can't do it with less. So hopefully that makes sense. And now let's take a look at the code. And it's kind of a lot of code, so I'd rather just go through instead of coding it live. So standard union find that you can just like copy paste on anywhere on LeetCode. So you have roots and ranks, and you have a component. This is what I added. This is like the thing that we added here. That isn't in a standard union find. You just initialize everything with a root of itself and a rank of 1, and then a standard find function. And then in the union function, you check for your 2 nodes, do they have the same parent? If they have the same parent, they're already connected, so we don't need to make a union. And then otherwise, you just figure out which way to connect it. And for every successful connection, like I said, you have 1 less component. And then the actual code is basically, first, we're going to make a union find for Alice. Then we're going to make a union find for Bob. Then we'll keep a track of how many redundant edges we have. So first, we're going to go through all of the edges that are type 3. And we're going to get a Boolean of, did that edge connect something in Alice? Did that edge connect something in Bob? If it connected something in one of them, that's not redundant, and that's going to be fine, and we can use it. But if it didn't do anything for any of them, then that edge is redundant, and we can increase the result. Then we go through the rest of the edges. If it's a type 1 edge, we check, did it do something in Alice? We'll try to use it for Alice. And then the reason I have these is because the edges are from 1 to n, and then the nodes in a union find are 0 to n minus 1. You can modify it if you want to, but yeah. So you just check for Alice, like, did this do anything? Was this a successful union or not? Successful union is going to return true. Failed union is going to be false. So if it's a failed union, this was already connected and this edge is redundant, so we just increase the result. Same thing for Bob. Then finally at the end, we just check, does Alice only have 1 component, meaning we have n-1 successful unions for Alice and n-1 successful unions for Bob. If that's the case, then Alice and Bob are fully connected, so we can return how many redundant edges we had. Otherwise, they're not fully connected, so we can just return -1. And so we can run that. Yeah, I think I was doing some other stuff, but yeah, it didn't take too long. Like, I think it took, you know, if I was to like do it from scratch, probably takes less than 20 minutes. Like, it's pretty straightforward. It's just, and you will have union find problems actually that you will have to make slight modifications. So this is one. There's some other ones like group them or something. So it is kind of useful to understand how union find works. So if you need to add a little bit to it, you can. Like this thing to get how many components was like relatively easy. There's some other stuff you have to do as well and some other problems. So here we go, and it does work. Okay. And yeah, basically this union find, other than this components thing, so like this line of code, this line of code, and this line of code, can just be copy pasted from anywhere. I try to write it from scratch once in a while, so I wrote it from scratch today. But usually I copy paste it like 9 out of 10 times because it's pretty straightforward and I've done it and I can do it if I need to. Yeah, so let's talk about time and space and all that stuff. So we're going through all the edges twice, right? Like we're going through all type 3 edges and then the other ones. There's no point in doing a sort because you only need to go through twice. So it's going to be faster to just go through twice. So to make a union find is O of n already. And then for each edge, we try to make a union, which is roughly O of 1. I think it's like 1.2 or whatever it is. Yeah, you can look it up. I think it's like the Ackermann function or something like that, which is roughly O of 1. So like a find for a node is in O of 1. A union for a node is roughly in O of 1 on average. In worst case, I guess. And then, so basically, if for every edge you do 2 unions or whatever, then this is just going to be linear time. And then space. So I think it's O of n. Let's just see. So what are we using here? So in a union find, you use a roots array and a ranks array, which is O of n, because it keeps track of every node. So those are O of n. I think that's mostly it. Components is just an integer. Yeah, and each one of these uses, yeah, roots and ranks. We didn't really do anything to the edges, I think. Oh, actually, so this time will be this time will be a little different. It's not n because so to make a union find, like the union find is based on n, which is this n, and then this thing is based on the edges. So for every edge, you do a union or a find. So it's actually technically like n plus e, where e is the length of edges. So or people you'll see it a lot like this, v plus e, which is like the vertices and the edges, and a vertex is a node, and then edge is like one of these. So you see this format a lot too. So yeah, space. So you will have the vertices because, like I said, a vertex is a node. So each one of these is like, you're going to have n. So this will be n space and this will be n space. But I don't think we store anything from edges. So I don't think edges is going to affect space complexity here, I believe. At least I'm not seeing anything. Yeah, and so I think it's this. Nice thing is we can try running this guy and see. Or it might be too big. Okay, so it's n plus e, which is what I said, and n, which is, yeah, so n, v, same thing. So this is basically n, where n is this number here. So it's the same thing. Yeah, and it's a relatively straightforward graph problem, I think. I think you can do it without doing disjoint set, but learning the disjoint set for graph, like, if you have avoided learning it, it's not very hard. Like, it's a pretty easy one to learn, and it makes a lot of problems a lot easier. So definitely would recommend learning it instead of trying to do like depth first search or breadth first search and just like refusing to ignore it. It's definitely one of the easier algorithms to learn. You basically just have to you just have to remember the like how this thing works, and which took me like a few days or something. It's not hard at all, and it's pretty intuitive how all this stuff works, and definitely is going to be the easiest route by far in a lot of graph problems. So I would recommend. But yeah, it's going to be all for this video. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And yeah, it shouldn't be missing any more in the near future. So thanks for watching, and I'll see you in the next one.